These are radio waves coming from Jupiter, the largest planet in the solar system, constantly emits powerful radiation bursts millions of miles into space. Wind speeds here reach more than 400 m per hour, 180 m per second. The planet itself is enormous. Its diameter is more than 11 times larger than Earth's. Storms here stretch tens of thousands of miles across, large enough to swallow our entire planet. For decades, scientists believed they understood this world, a giant sphere of hydrogen and helium with a small core hidden deep inside. However, recent measurements are beginning to challenge this picture. Chemical analysis shows that Jupiter should contain a large amount of oxygen, most of which is locked in water. Gravity measurements indicate that most of the heavy materials are located deep inside the planet. Magnetic mapping reveals powerful currents moving thousands of miles beneath the clouds. Each of these results was obtained using precise instruments. Each of them has been verified multiple times. And yet, when scientists try to combine them, the picture stops making sense. Something inside the planet is behaving differently than the models predicted. The measurements do not agree with each other. And this raises a deeper question. What's really happening inside Jupiter? Over the past few years, a number of new studies have begun to change our understanding of Jupiter's internal structure. And when their results are placed side by side, they begin to suggest that the interior may be far less uniform than previously thought, and the first clue comes from something scientists expected to find in abundance. Water. According to the standard models of planetary formation, Jupiter should contain a large amount of oxygen locked in water molecules. Much of this material should be mixed into the atmosphere and detectable through chemical measurements. However, recent studies suggest the signal may be weaker than expected. In 2026, a study by a collaboration of American scientists led by Yahun Yang combined chemical kinetics with large-scale atmospheric transport models to estimate how oxygen moves through the planet's atmosphere. Instead of analyzing the chemistry in isolation, the team linked chemical reactions with vertical mixing and atmospheric circulation. Yang and his colleagues tested several scenarios for the oxygen content in the deep layers of Jupiter's atmosphere. The red dot shows the actual amount of carbon monoxide measured in Jupiter's atmosphere. Different atmospheric models can reproduce this value depending on how efficiently gas is mixed between the deep layers and the upper atmosphere. However, chemical models rule out the most extreme scenarios. The result pointed to a surprisingly modest enrichment in oxygen, about 1 to 1.5 times the solar value. For a giant planet that likely formed beyond the snow line where icy material was abundant, this is unexpectedly low. If Jupiter had accumulated a large amount of water during its formation, the atmosphere should reflect that history. However, the chemical signal tells a different story. This raises a deeper possibility. Most of the heavy material, including water, may not be evenly mixed in the observable atmosphere at all, but the atmosphere can only tell us what's happening near the clouds. If water and other heavy elements are hidden deeper inside Jupiter, how can scientists detect them? To explore the deeper layers, scientists turned to a completely different type of measurement. They measured how Jupiter's gravity affects a spacecraft flying by. According to atmospheric chemistry data, the measurable oxygen content may be only moderate. However, this conclusion is based on an important assumption that the planet is well mixed from top to bottom. Recent studies of the planet's internal structure call this assumption into question. In the review of Jupiter's formation and internal structure published in the journal Icarus in 2022 and led by Rabbit Hillid, models reproducing the gravitational field measured by the Juno spacecraft were analyzed. These models show that Jupiter's interior may contain strong compositional gradients rather than a uniform mixture. In other words, heavy elements may be distributed unevenly throughout the planet. Traditional formation models predict a relatively small region of concentrated heavy material, a core containing about 10% of the planet's mass. However, interior structure models that reproduce the gravitational measurements from the Juno spacecraft allow for a completely different configuration. In some solutions, the region enriched with heavy elements could contain up to 30% of the planet's mass or even more. Instead of a compact core, the planet may contain an extensive inner region where heavy elements are diluted with hydrogen and helium over a much larger fraction of the planet's radius. Planetary scientists often describe this structure as a diluted or fuzzy core. In such a configuration, heavy elements are not confined to a small central object. They are distributed across a large portion of the interior. If such a structure exists, the chemical composition measured in the upper atmosphere may not reflect the composition of the entire planet. Material located deeper inside could remain partially isolated from the regions where chemical measurements are taken. A moderate oxygen abundance in the atmosphere would then no longer imply that Jupiter has little water overall. It could simply mean that some of the oxygen is locked deeper within the planet. At this stage, the research leads to a new question. If Jupiter contains internal barriers that limit mixing between layers, what exactly creates these barriers? Can they be detected directly? And if such barriers exist, shouldn't they affect not only the atmospheric composition, but also the planet's internal dynamics? The next clue lies in the very way Jupiter generates its magnetic field. Unlike atmospheric chemistry, the magnetic field is generated deep within the planet. It carries information about the motion of electrically conducting material hidden far beneath the clouds. Using data from dozens of polar flybys of the Juno spacecraft, researchers have built one of the most detailed models of Jupiter's magnetic field to date, the JRM-33 model. The measurements are precise enough to describe the field structure down to the final spatial scales. In the same study, the outer boundary of Jupiter's main magnetic dynamo is estimated to be at roughly 0.81% of the planet's radius. At this depth, the pressure is so high that hydrogen becomes electrically conducting. Convection in this metallic hydrogen layer generates the magnetic field. Any stratification or stability at these depths would affect the formation and evolution of the field, and these changes can be detected by Juno's magnetometer. At first glance, the magnetic field should be roughly dipolar on large scales, but one feature immediately breaks this symmetry. Near the equator lies a powerful magnetic anomaly known as the Great Blue Spot. This anomaly marks a region where the magnetic field emanating from the dynamo is unusually intense. Even more interesting is what happens when the new magnetic maps are compared with earlier ones. Between successive models derived from Juno's data, scientists have detected small but measurable changes in the magnetic field near this region. This phenomenon is known as secular variation. The most consistent explanation links these changes to deep atmospheric motions. According to the model, Jupiter's zonal winds may extend to a depth of about 2,000 miles below the upper cloud tops. At such depths, hydrogen is sufficiently conductive for the moving fluid to drag magnetic field lines along with it. The observed magnetic changes are consistent with flows moving at about 1/12 in per second. This speed may seem slow, but on the planetary scale, it is enough to alter magnetic structures over time. This finding shows that Jupiter-Andropos' atmosphere and its magnetic dynamo are not isolated systems. They are dynamically connected. Taken together, the magnetic and gravitational measurements converge at the same depth, roughly 2,000 meters beneath the clouds. Above this level, atmospheric circulation and cloud chemistry dominate. Below this level, the increase in electrical conductivity allows magnetic forces to influence the motion of the fluid itself. This transitional zone may act as a natural boundary within the planet. Material transported by weather systems above may not mix freely with the deeper layers below. If such a barrier zone exists, it explains why chemical measurements in the atmosphere, such as oxygen estimates derived from carbon monoxide, may not match the distribution of heavy elements predicted by interior models. The boundary lying thousands of miles below the clouds is invisible to the eye. But what dominates the view is the storm, the Great Red Spot. However, in our investigation, the vortex is not considered as a spectacle. It becomes a test of depth. Back in 2021, researchers used Juno-Andropos gravitational measurements during close flybys of the storm to estimate how far the vortex extends beneath the cloud tops. The result was surprisingly shallow. Microwave measurements show that the storm structure reaches pressures of about 100 bars, corresponding to a depth of roughly 150 meters. Gravitational measurements set a broader range of 125 to 300 meters beneath the clouds. This is much shallower than Jupiter-Randapos jet streams. The major atmospheric jets detected by Juno extend 2,000 miles downward. In other words, the planet Tandapos' most famous storm occupies only the upper portion of the dynamic atmosphere. Thus, the surrounding jet streams are in order of magnitude deeper than the vortex itself. This reveals something important about the planet. The Great Red Spot is not a window into the planet Tandapos' depths. Tandapos, a structure embedded in the upper layers of a much larger circulation system. This means that the visible atmosphere cannot directly reveal where Jupiter-Randapos heavy elements or water reservoirs are located. Such processes occur far below the depth reached even by the largest storms. Another question concerns the age of the vortex. For centuries, it was believed that the Great Red Spot had been observed continuously since the 17th century. However, an analysis of historical observations conducted in 2024 suggests a different scenario. The permanent spot, which was recorded by Giovanni Cassini between 1665 and 1713, was likely a different atmospheric feature. The modern Great Red Spot was most likely first observed in 1831. Researchers have considered several possible causes for the storm. One scenario involves the merging of several large vortices. Another suggests the aftermath of a powerful atmospheric storm. But the most likely explanation links the vortex to disturbances in Jupiter-Randapos' zonal jet streams. According to this view, the storm formed when the shear flow between neighboring jets became unstable. This interpretation brings the focus back to the same structures highlighted in previous clues: deep atmospheric jets. They organize circulation thousands of miles deep. They influence the magnetic field, and in the upper layers of the atmosphere, they can create long-lived storms like the Great Red Spot. When chemical, gravitational, and magnetic measurements provide different pieces of information, another parameter becomes crucial: the precise size and shape of the planet itself. The shape of a rotating planet directly depends on how mass is distributed within it. And this brings the investigation back to the same unresolved problem: the location of heavy elements and water on Jupiter. Speak. In 2026, researchers used radio signals from the Juno spacecraft to refine the measurements of Jupiter's shape. As the signal passes through the atmosphere, it bends and slows slightly. By analyzing the delay in frequency shift of the radio waves, scientists can reconstruct the atmospheric structure and determine the planet's precise curvature. The result is a small but significant adjustment. Estimates suggest that Jupiter is roughly 5 miles narrower at the equator and about 15 miles more flattened near the poles than previously thought. Even such small differences matter because the planet shape is directly built into interior structure models which aim to reconcile data on gravity, winds, and the magnetic field. At this stage, the investigation already contains several independent clues. But now, every model of Jupiter must satisfy all these constraints simultaneously. Gravity shows how mass is distributed. Magnetic measurements reveal motion in the conducting inner layer. Atmospheric chemistry probes the upper layers. Storms indicate the depth of visible weather. The planet shape ties all these pieces together. Each method examines a different depth, which is why the results may appear contradictory. They do not probe the same part of the planet. Chemical tracers constrain oxygen where carbon monoxide remains stable. Gravity allows expansion of the region enriched with heavy elements. Magnetic measurements show winds reaching the conducting inner layer. Storms like the Great Red Spot remain confined to the upper atmosphere. All of this evidence points to a planet whose interior is layered, dynamic, and still only partially explored. So where are Jupiter's heavy elements and water actually concentrated? They reside within an extended mixture of a diluted core below the boundary reached by the deep winds, or they are distributed in layers that none of our measurements can fully probe as yet. Jupiter floats in the darkness like a colossal beacon. From afar, it looks like a striped sphere, a gas giant so massive that it outweighs all the other planets in our system combined. What kinds of forces create those alternating shades of orange and white? Today's journey is not just about a planet, but a dynamic laboratory where atmospheric physics and planetary evolution converge. This giant, composed mostly of hydrogen and helium, the very ingredient stars are made of, never ignited into a star. Instead, it radiates an internal glow, a quiet testimony to its turbulent origins. What drives this internal heat? How do the powerful winds carved across its surface maintain the continuous motion we observe? Today, we'll take a closer look at its faint halo of rings and distant moons lost in the glare of the giant. What stirs in the depths of this planet? Where have the obvious surface elements gone? What illogical phenomena are hidden at its poles? Our journey, accompanied by original imagery from NASA probes and enriched with meticulous animation, invites exploration of these mysteries. Up close, Jupiter's face breaks into bright bands of clouds, ochre brown belts and pearly white zones running parallel to its equator. These atmospheric stripes are not static markings, but visible manifestations of powerful jet streams racing around the planet at immense speeds. Jupiter's atmosphere is organized into east-west flows that alternate as they encircle the globe, intensifying multiple times from the equator to the poles. In the lighter zones, clouds of ammonia ice rise from below, reflecting sunlight and white and pale gold. In the darker belts, we see deeper layers of the atmosphere where clouds tinted by compounds like ammonium hydrosulfide give off rusty and amber hues. Each adjacent band moves in the opposite direction of its neighbor, a giant planetary pattern etched by ferocious winds. The speed of these jet streams can reach hundreds of miles an hour, far exceeding any hurricane on Earth. Speak some winds. In Jupiter Andropos, upper cloud layers exceed 400 miles per hour, and at certain altitudes even more. The Coriolis effect on this rapidly spinning sphere fractures the atmosphere into dozens of east and west moving jets, between which lie the bright zones and dark belts. The Planetandropos atmosphere is divided into zonal flows, essentially a system of cyclonic and anticyclonic jet streams. Deep below, Jupiter Andropos's internal heat left over from its formation drives convection that continuously fuels these flows, sustaining eternal winds. The jet streams form sharply defined bands that remain astonishingly stable over time. Yet their boundaries are turbulent and chaotic. We observe fine waves and curls where fast winds whip past each other, a sign of intense wind shear shaping the cloud tops. Ammonia and water vapor rising upward condense into bands of high white clouds, while in other areas descending air clears the sky to reveal the dark layers beneath. The result is a marbled pattern encircling the entire planet. Amid Jupiter Andropos spans, there is a storm raging like no other. The Great Red Spot, this salmon-colored oval cyclone, has been raging in the planet Andropos, southern hemisphere, for centuries, and Itandropos, large enough to engulf Earth entirely. More precisely, the Great Red Spot is an anticyclone, a high-pressure vortex spinning counterclockwise opposite to a typical cyclone and towering above the surrounding cloudscape. In this close-up, the Spatandropos clouds swirl into a dense oval ring, the color of a faded brick. A high-altitude haze gives the spot its reddish tint, though its exact chemical makeup remains somewhat mysterious. It may be colored by complex organic molecules or phosphorus-bearing compounds dredged up from the depths. Inside, bands and swirls spiral like a giant eye. Around its edge, winds rage at speeds of up to 268 miles per hour, sculpting cloud matter into a form that has fascinated astronomers since it was first observed over 150 years ago. White ammonia clouds swirl around the Spatandropos perimeter, stretching and being pulled into the vortex. From time to time, smaller storms collide with the Great Red Spot, either bouncing off or being absorbed. It acts as a ruler of Jupiter Andropos' atmosphere, influencing weather far beyond its immediate borders. In recent decades, observers have noted that the spot is gradually shrinking and changing shape. It was once twice its current size. Nevertheless, it remains the largest storm in the solar system. The Great Red Spot completes a rotation roughly once every 6 Earth days. At its center lies a relatively calm area compared to the fierce surrounding jets. High above the storm hovers a dome of reddish haze, setting it apart from the brighter zones nearby. Within this giant, lightning has occasionally been observed, briefly illuminating the clouds from within. Far beneath the cloud tops, the storm likely extends for many miles, though instruments aboard the Juno spacecraft suggest it may be relatively shallow compared to the planet Andropos's radius. Still, it stands significantly taller than the surrounding cloud layers. The Great Red Spot is essentially a massive, long-lived high-pressure system. something akin to a hurricaneandapos inverse with winds spiraling at its top. Etandapos persisted so long that it may have even changed form over time, merging with several major storms from centuries past. Beyond the great red spot, Jupiterandapos' entire atmosphere is filled with smaller storms and vortices. Planet is a canvas of ever-changing turbulence. Along the belts we find elongated white ovals, small anticyclones similar in nature to the great red spot, but much smaller in size. Some last for decades, while others form and dissipate within a few weeks. At one latitude, a chain of such storms curved around the Planetandapos, southern hemisphere, like a string of pearls. These white ovals can merge over time. In 2000, 3 small ovals combine into a larger storm called Oval Ba. Speak. Oval Ba, nicknamed Red Spot Jr., later turned red and reached a size roughly half that of the Great Red Spot. Between the major spots, Jupiter's clouds are full of turbulent flows. At the boundaries of the fast jet streams, the wind shear creates twisting filament-like patterns. We observe swirls where dark belts meet light zones, and likely these are Kelvin-Helmholtz waves formed when 2 air layers slide past each other, creating a wave-like cloud. In some regions within the belts, small dark barges drift by, while bright pop-up clouds resembling popcorn mark powerful convective thunderstorms rising upward. Jupiter's atmosphere has no solid surface to interrupt the winds. Storms can dive deep and last longer than any earthly equivalent. Following the curve of the planet, we see countless small rotating structures from compact vortices just a few hundred miles across to vast chaotic regions where multiple vortices interact. These collisions and mergers regularly disrupt the rest of the strike pattern. For example, a turbulent region often trails behind the Great Red Spot, where the spot's flow disrupts the neighboring belt and creates clumps of vortices and pale clouds. This turbulence acts as a storm nursery. New vortices can be born in these chaotic shears. Yet, amid this apparent chaos, there is a kind of order. Each storm tends to stay within its latitude band, held in place by powerful zonal jet streams. Despite the striped and chaotic look of Jupiter's equatorial and mid-latitude regions, surprising order emerges at the poles. Flying over the poles, Juno discovered polar cyclones arranged in geometric symmetry. At Jupiter's North Pole, 8 massive cyclones are evenly distributed around the central one, forming a near-perfect octagon of storms. Each of these polar cyclones is enormous, about 1,500 to 800 meters across, but they sit tightly next to each other without merging. All spin counterclockwise, their spiral arms nearly touching, yet balance is maintained as if something repels them from each other, so no one crowds too closely. The pattern is truly striking, a polygon of synchronized cyclones, bizarre yet stable. The South Pole displays a similar scene. It originally had 5 cyclones surrounding a central one and was later joined by a 6th forming a hexagon. These polar clusters have remained stable for years of observation, barely shifting. The symmetry suggests hidden physics. Perhaps a fine balance of vortex flows and jetreme boundaries locking the storms into place. Suddenly, a bright flash lights up the planet's clouds. There's lightning on Jupiter. For a moment, the tops of the clouds just glow intensely. Then darkness returns. Jupiter's thunderstorms produce lightning that rivals and even surpasses that of Earth. Since Voyager first spotted them in 1979 as fleeting flashes atop the clouds, we've known that lightning on Jupiter occurs deep in the layers of water clouds where temperatures and conditions are similar to Earth's storms. But NASA's Juno mission found a new twist. The planet also has shallow lightning. That's electrical discharges high in the atmosphere within clouds made not just of water, but of an ammonia-water mixture. In these cold upper layers where temperatures drop to about minus 126 degrees Fahrenheit, normal liquid water can exist. But Jupiter's abundant ammonia acts as antifreeze. During powerful storms, icy hailstones are hurled upward some 15 miles above the usual cloud decks into regions rich in gaseous ammonia. Ammonia melts the ice, forming droplets of ammonia water slush. In this strange alien thundercloud, collisions between rising ice crystals and falling hailstones saturated with ammonia, which earned the nickname mushballs, generate static electricity. The result, lightning crackling through Jupiter's upper atmosphere, far higher than we thought lightning could form. Speak, these shallow lightning bolts flash through ammonia clouds, briefly illuminating towering storm structures with eerie blue and gold light. Juno detected these flashes on the planet Tandapus, night side, each lasting just milliseconds, yet glowing nearly as brightly as Earth Andapus, familiar lightning strikes. Deeper down in more conventional thunderstorm regions 30 to 40 miles below the cloud tops, lightning strikes are just as fierce. Here, water exists in all three phases: ice, liquid, vapor, just like in Earth Andapus. Cumulonimbus clouds promoting energetic charge separation. Some lightning bolts are colossal, releasing several orders of magnitude more energy than typical lightning on Earth. Juno detected thousands of lightning flashes, hearing their radio crackle, so-called whistlers, as it flew over the cloud tops. Interestingly, it was Juno Andapus' discovery of shallow lightning that solved the mystery of why ammonia seemed to be missing from Jupiter Andapus air. Mushball hailstones were carrying the ammonia deep down, removing it from the upper atmosphere. Once more, we witness a flash piercing a distant cloud bank. Lightning illuminates billowing cloud towers rising above the surrounding haze. These convective towers can reach heights of 30 minutes, driven by the planet Tandapus' internal heat. In the brief glow, we glimpse the outline of a colossal thunderhead, possibly the source of ammonia-rich hail falling downward after the strike. Now let Tandapus go beyond the clouds and storms. High above the poles of Jupiter, there are shimmering auroras of staggering power dancing in the sky. Each pole is surrounded by the constant halo of glowing auroral radiation, crowning the planet Tandapus, darkness with an otherworldly blue-violet light. Jupiter Andapus auroras are the most intense in the solar system, hundreds of times more energetic than Earth Andapus's northern lights. Unlike the fleeting auroras on Earth that appear only during solar storms, here the auroras never cease. The Andapus, ray-driven not only by the solar wind, but also by the planet Tandapus' immense magnetic environment. Jupiter has a magnetic field estimated to be between 16 and 54 times stronger than Earth Andapus, generated by metallic hydrogen rotating deep within the planet. This magnetic field captures charged particles and channels them toward the poles. When these high-energy particles collide with Jupiter Andapus's upper atmosphere, they excite hydrogen molecules, causing them to fluoresce in ultraviolet and infrared light. The result, gigantic oval rings of auroral light encircling each pole. In the image, the northern aurora glows with an electric blue light spiraling under the influence of magnetic forces. The auroras are partly powered by the rotation of the planet and its moons. Volcanoes on Io, Jupiter Andapus' innermost major moon, spew tons of ionized sulfur and oxygen, which get trapped in Jupiter Andapus' magnetic field. As Jupiter rotates, taking less than 10 hours, it drags the magnetosphere with it, flinging ions toward the poles. The Andapus' contribution is so significant it creates footprints in the aurora, bright spots corresponding to magnetic connection points between Io and the planet Andapus' atmosphere. Similar footprints come from Europa and Ganymede. One of these can be seen as an especially bright, pulsating auroral spot at the edge of the northern oval. In addition, bursts of solar particles, the solar wind can intensify the glow, causing it to flare even brighter and more dramatically. Observations from Hubble have shown auroral curtains reaching thousands of miles above the cloud tops, far surpassing anything we Andapus have ever seen on Earth. However, even an observer standing within Jupiter Andapus' atmosphere would not be able to see these massive glowing rings overhead, the Tandapus, because they glow in wavelengths that our eyes can Andapus perceive, primarily ultraviolet. On top of that, they also emit X-rays, essentially Jupiter Andapus, aurora shimmer, emitting high-energy X-rays, a phenomenon still being studied to determine how these particles are being accelerated. Speak. Let's pull back even farther from the planet's surface. Against the blackness of space, Jupiter is surrounded by something unexpected, a faint set of rings encircling the gas giant, shimmering like strands of spider silk. Jupiter's rings are nothing like Saturn's bright sweeping arcs. These are thin, almost transparent bands of dust, so tenuous they weren't discovered until 1979. In this image, we see the main ring as a slender, bright line wrapping around the planet's equator, a dim halo within it, and a wide, diffuse gossamer ring extending outward. These rings sparkle in sunlight, appearing as a faint white line crossing Jupiter's night side. They are 1,000,000 times fainter than the planet itself and are composed of tiny dust grains, not brilliant chunks of ice. So what maintains such structures around the colossal planet? The answer lies right in orbit: Jupiter's small inner moons. Two of these, Amla and Adraya, appear as faint points of light within or near the rings. In this image, Amalthea is visible on the left edge of the ring system, a tiny white dot with a barely noticeable diffraction spike, confirming its presence in JWST's infrared view. The even smaller Adia appears as a speck of light on the very edge of Jupiter's main ring. These rings exist because the moons are constantly replenishing them. Unlike Saturn's icy rings, which may be remnants of a shattered moon, Jupiter's rings are formed from dust created by micrometeoroid impacts. When space debris strikes the surface of tiny moons like Adraya or Metis, it kicks up particles that drift into orbit around the planet, and over time, countless impacts form a dust ring. Adrisya, only about 12 miles across, orbits right at the edge of the main ring and is its primary material source. The slightly larger Metis, though not shown here, contributes as well. Farther out, the moons Amma, about 155 miles wide, and emit dust that forms the faint outer braids of the ring. Data from the Galileo spacecraft confirm this mechanism. Jupiter's rings are indeed composed of dust blown off its small moons. The vertical thickness of the main ring is just a few miles. Up close, the particles are microscopic bits of silicate rock, likely dark in color, which is why they reflect so little sunlight. They're virtually invisible unless seen in infrared or angled and with backlighting as we're doing now. There it is, Jupiter, a dynamic system in its own right. Atmosphere, magnetosphere, rings, and moons all bound in a complex gravitational and electromagnetic embrace. We observe atmospheric bands stretching across its latitudes, holding storms and channeling energy from within. We feel its internal heat still radiating from a primordial furnace, fueling convection that gives rise to thunderstorms and towering clouds. Invisible lines of magnetic force reach from its depths, linking to the auroras at the poles and coursing through Io, driving electric currents that make the polar skies glow. Jupiter's rotation ties all these elements together. Its rapid spin shapes the bands, aligns the cyclones, shifts the magnetic field, and even helps maintain the rings in a flattened disk. From this perspective, the planet is a symphony of motion and forces, fluid dynamics, electricity, magnetism, gravity, all playing out on a grand scale. Now all these elements come together in a single portrait. Jupiter is a world of eternal change and immense power. There's no need for a conclusion because whatever we say, Jupiter remains what it has always been: a majestic, mysterious, and forever dynamic gas giant, holding with it echoes of creation and the ongoing drama of the cosmos.